have studied the equations for reluctance of air gap under various conditions. So now we have to derive an expression for the MMF of air gap. So first let us consider the smooth air gap. So we know that air gap will be smooth when both the stator as well as the rotor are having smooth surfaces. So let us derive an expression for the MMF of a smooth air gap. So we know this parameter H. So in the basics we have studied this parameter H, which is known as the magnetic field strength or magnetizing force or magnetic field intensity H. We have defined this parameter H as the MMF per unit length Ni divided by L. So H is the MMF per unit length Ni divided by L. So this can be denoted as small letter at. So here in this section we will be denoting the MMF per unit length as small letter at. We know that the total MMF, whose unit is ampere turns, can be denoted as capital letter at. So we will denote the MMF per unit length H as small letter at. So if we can calculate the value of this H, then by multiplying H with the length of air gap, we will get the value of MMF. H into L gives Ni, the total MMF. So let us calculate H. So we know another equation of H, that is H is equal to B, the flux density B divided by absolute permeability mu. So if we use this equation, we will get the value of H, and then by multiplying that H with air gap length L, we can calculate the MMF. So the MMF per unit length of air gap, that is ATG. G means the gap. So ATG is equal to B by mu. So here we are using the average flux density in the air gap, B average, divided by mu. So in case of air gap, mu is equal to mu 0 into mu r. Mu r is 1 for air. So we are using mu 0 only. So substituting the value of mu 0, which is equal to 4 pi into 10 raised to minus 7. So on calculating the value of 1 divided by 4 pi into 10 raised to minus 7, we will get it as approximately equal to 8 lakhs. So the equation will be 8 lakhs into B average. So this is the MMF per unit length. So by multiplying this MMF per unit length by the total length of air gap Lg, we will get the value of total air gap MMF, and that equals 8 lakhs into B average into Lg. So now, so we know the air gap will not always be smooth. So we have to consider the MMF of air gap in machines with open armature slots and radial ventilating ducts. So we have studied the reluctance of air gap under these conditions. Reluctance of both smooth air gap and reluctance of air gap with slots and ducts. We have derived those equations. So there we have seen that the reluctance of air gap with slots and ducts is more than that of a smooth air gap. So I have noted the equations here. So the first equation, Sg is equal to Lg divided by mu 0 L into Ys. This is the equation corresponding to a smooth air gap, and this is the equation for an air gap with slots and ducts. So here by comparing these two equations we can see. So here it is Ys, here it is Ys minus Kcs Ws. So denominator is reduced here, so reluctance will be more here. So with slots and ducts, the reluctance of air gap will be more. So now we know another parameter Kg. We have defined a constant Kg known as total gap contraction factor, and it was the ratio of reluctance of air gap with slots and ducts to the reluctance of smooth air gap without ducts, and that ratio equals Kg. Okay. So സ്ലോട്ട്സും ഡക്റ്റും ഉള്ള കേസിലെ എയർ ഗ്യാപ്പിൻ്റെ റിലക്റ്റൻസും സ്മൂത്ത് എയർ ഗ്യാപ്പ് ഡക്റ്റും ഇല്ലാത്ത സ്മൂത്ത് എയർ ഗ്യാപ്പിൻ്റെ റിലക്റ്റൻസും തമ്മിലുള്ള റേഷ്യോ ആണ് കെ ജി. So from here we can see that the reluctance of air gap with the slots and ducts is equal to kg into reluctance of smooth air gap without ducts. That is, reluctance of air gap with the slots and ducts is kg times more than that of smooth air gap without ducts. So we know another equation for MMF. So MMF is equal to AT is equal to S into phi. MMF is equal to S into phi. MMF is directly proportional to the reluctance. MMF is directly proportional to the reluctance. So in case of smooth air gap, let us assume that the reluctance is S. And in case of air gap with the slots and ducts, the reluctance become kg into the reluctance of smooth air gap without duct. സ്ലോട്ടും ഡക്റ്റും ഉള്ള കേസിൽ ഈക്വേഷൻ നോക്കിയാൽ നമുക്കറിയാം സ്ലോട്ടും ഡക്റ്റും ഉള്ള കേസിലെ എയർ ഗ്യാപ്പിൻ്റെ റിലക്റ്റൻസ് സ്മൂത്ത് എയർ ഗ്യാപ്പിൻ്റെ റിലക്റ്റൻസിൻ്റെക്കാളും kg ടൈംസ് മോറാണ്. സോ MMF എന്ന് പറഞ്ഞാൽ റിലക്റ്റൻസിന് ഡയറക്റ്റ്ലി പ്രൊപ്പോർഷണലാണ്. സോ റിലക്റ്റൻസ് kg ടൈംസ് ആവുമ്പോൾ MMFും എന്താവും kg ടൈംസ് ആവും. സോ ദ ഇക്വേഷൻ ബിക്കംസ് 8 lakh into B average into LG into kg. സോ സ്ലോട്ടും ഡക്റ്റും ഉള്ള കേസിലെ റിലക്റ്റൻസ് സ്മൂത്ത് എയർ ഗ്യാപ്പിൻ്റെ കേസിലെ റിലക്റ്റൻസിനേക്കാളും kg ടൈംസ് കൂടുതലാണെങ്കിൽ ആ കേസിലെ MMFും സ്മൂത്ത് എയർ ഗ്യാപ്പിൻ്റെ കേസിലെ MMFിനേക്കാളും kg ടൈംസ് കൂടുതലായിരിക്കും. ബിക്കോസ് MMF ഇസ് ഡയറക്ട്ലി പ്രൊപ്പോർഷണൽ ടു റിലക്റ്റൻസ്. സോ ടോട്ടൽ MMF ബിക്കംസ് kg ടൈംസ് ദ MMF ഓഫ് smooth air gap, that is 8 lakh into B average into kg into Lg. So now, so see this equation here, 8 lakh into B average is the MMF per unit length. So we have initially calculated the 8 lakh into B average as the MMF per unit length of air gap. So here ATG is equal to MMF per unit length into total length. We are usually calculating MMF like that. MMF per unit length into total length. That means this term kg into Lg denotes the effective length of the air gap. Kg into Lg is the effective length of the air gap, and it can be denoted as LGE, Lg effective, which is equal to kg into Lg. And we know this gap contraction factor kg is always greater than unity, and hence the effective gap length LGE will be greater than Lg. And in that sense, we can call this constant kg as the gap expansion factor. Because the multiplication of Lg with kg resulted in an increase in the value of air gap length, air gap length. Actual air gap length LGയെ kg എന്ന് പറയുന്ന കോൺസ്റ്റൻ്റ് കൊണ്ട് മൾട്ടിപ്ലൈ ചെയ്തപ്പോൾ കിട്ടിയ എഫക്റ്റീവ് ലെങ്ത് എന്ന് പറഞ്ഞാൽ കൂടുതലാണ് ആക്ച്വൽ എയർ ഗ്യാപ്പ് ലെങ്തിനേക്കാളും. സോ വി ക്യാൻ കോൾ ദ കോൺസ്റ്റൻറ്റ് kg ആസ് ഗ്യാപ്പ് എക്സ്പാൻഷൻ ഫാക്ടർ. സോ നൗ ലെറ്റ് us see another modification. So this was our equation. ATG is equal to 8 lakh into B average into kg into Lg. So here we know the flux density is equal to flux divided by area. So I have replaced B average as phi divided by Ag, flux divided by area of air gap. Now this can be rearranged like this. I have taken this kg to the denominator side, can be written as Ag divided by kg, and this Ag by kg is represented as Ag dash. And this area Ag dash is known as the contracted gap area, the contracted gap area Ag dash, which is equal to Ag divided by kg. Now why it is called as contracted gap area? Because we have substituted Ag dash in terms of Ag divided by kg, and we know that kg is greater than 1. So when we divide Ag by kg, we will get the value that we get, that Ag dash will be less than Ag. That is why it is called as contracted gap area. AG by kg നമ്മൾ ചെയ്യുമ്പോൾ kg greater than 1 ആയതുകൊണ്ട് കിട്ടുന്ന ആൻസർ ദാറ്റ് ഈസ് AG ഡാഷ് എന്ന് പറയുന്നത് AGയേക്കാളും കുറവായിരിക്കും. അതുകൊണ്ടാണ് AG ഡാഷിനെ കോൺട്രാക്റ്റഡ് ഗ്യാപ്പ് ഏരിയ എന്ന് പറയുന്നത്. So keep in mind these two equations. Effective gap length is equal to kg into Lg. Contracted gap area is equal to Ag by kg. We need these two for doing problems. Effective gap length and contracted gap area. Okay, now, so we have to consider the effect of saliency also. So we know some machines are having salient poles, projecting poles. We know salient poles are poles projecting outwards from the stator periphery. Okay. So here a salient pole machine is shown. So a salient pole is shown here. This is the pole body and the flux distribution in the air gap is also shown. So this is the air gap with a length Lg. So flux will be distributed like this. At the tip of the pole, flux will fringe around like this. And this is the flux distribution curve. The curve showing the distribution of flux. So flux density will be maximum at the center of the pole. So along the width of the pole body, the flux density is maximum, and that maximum value of flux density is denoted as Bg. Maximum flux density at the gap, Bg. Okay. And towards the interpolar space, towards the interpolar region, the flux density decreases. So flux is maximum under the poles, and poles in the interpolar space like flux density, fluxum korayum, so flux density korayum. So towards the interpolar space, the flux density decreases, and that at the interpolar axis the flux density reaches 0. So what is interpolar space and interpolar axis? Do you remember? So suppose a DC machine having 4 poles we have. So this space between 2 poles is known as the interpolar region, and the axis passing through the center of the interpolar region is known as the interpolar axis. So flux will be maximum under the poles, and towards the interpolar space flux reduces, and at the interpolar axis the flux will be 0. So like that, flux density is maximum under the pole and it reduces towards the interpolar space. So this will be the flux distribution curve, and the maximum value of flux density is denoted as Bg here, and the average value of this flux density is the B average, that is denoted here. This is B average. Now in case of salient pole machines, the effective gap length LGE is taken as kg sal into Lg. So kg sal is the gap contraction factor for salient poles. So here the effective length, while taking the effective length, we have to consider the effect of saliency also. So now, for calculating the MMF in salient pole machines, instead of taking the average flux density in the air gap, the maximum flux density at the center of pole, that is Bg, is considered. So in the previous case we have taken B average in the equation for MMF, but in the case of salient pole machines, as the flux density is not constant, we are using the flux density at the center of pole, the maximum flux density at the center of pole Bg. So equation becomes 8 lakh into Bg into kg into Lg. Instead of B average we have substituted Bg, and one more difference is there. Here the total gap contraction factor kg will be equal to kgs into kgd into kg salience. We have to take the effect of saliency also. So kg is usually equal to kgs into kgd. So here in case of salient pole machines, we have to take the effect of saliency also, that is kg salient. which is the gap contraction factor for salient poles. So that is the equation for MMF of air gap. ATG is equal to 8 lakh into BG into kg into LG. So this equation you have to remember. This is needed in the upcoming modules. So now, how will you calculate the value of BG? If we are asked to calculate ATG, we need the value of BG. So how to calculate BG? So we know a constant, there is a constant known as field form factor denoted as KF, which is the ratio of average density, average flux density over one pole pitch divided by maximum flux density in the air gap. So field form factor is average flux density divided by maximum flux density, that is B average divided by BG. So if we know both these values KF and B average, we will get the value of BG. So B average will be known for a machine. This is known as magnetic loading of a machine. So we will study it in detail in the next module. So B average will be known for all the machine. And if we know the value of KF also, we will get the value of BG. Okay. Now, how will you get the value of KF, the field form factor? So field form factor is approximately equal to psi. Now what is psi? For a machine, psi is the ratio of pole arc to pole pitch. Pole arc by pole pitch ratio is psi, and if psi is known, we will get the value of BG. BG will be equal to B average by KF, or B average divided by psi. Psi is pole arc divided by pole pitch. What is pole arc? So if this is a particular pole, this parameter is the pole arc, this length. This length is known as the pole arc. So pole arc divided by pole pitch. What is pole pitch? Distance between two adjacent poles is known as the pole pitch. So distance between two adjacent poles is the pole pitch, this one. So this pole arc by pole pitch ratio is the psi.